Welcome and thank you for joining me in this third of our four-part series on the Belimo energy valve. Today we will be discussing advanced valve control strategies. We'll be talking about flow control and power control, which are quite different from standard control philosophies of control valves. If you're new to the Belimo energy valve, the Belimo energy valve is a pressure-independent valve with a fully integrated BTU meter. This valve allows us to do a lot of extraordinary things, including measuring energy, managing delta T, and what we're going to discuss today, how to control directly to power output into your space. Let's begin with a small discussion of the evolution of the control valve. A traditional style control valve is what is known as a position control valve, and this means that the control signal directly controls how open or closed the valve is. What is shown here is a Belimo characterized control valve, but we could also have showed you a globe valve or any other type of traditional control valve. These valves are more or less open depending on the movement of the valve stem. This is the only thing that the controller controls. The problem with these types of valves is that while the valve may be open the same amount, we don't necessarily get the same amount of flow through that orifice. So if we think about a valve that's halfway open, receiving maybe only a 2 or 3 pound pressure drop, we're going to get a certain amount of flow. But that same valve, in the same half open position that was seeing 8 or 10 pounds of pressure drop, would obviously see a significantly higher amount of water. This is what makes a valve pressure dependent. The pressure causes variations in the actual flow value traveling through the valve and thus through the coil. Position control valves were the standard for a very long time in commercial HVAC operation. But within the last 10 or 15 years, a new type of valve has come into the marketplace, and this would be pressure-independent valves. Pressure-independent valves are what is known as flow control valves, which means that the control signal now directly controls the amount of GPMs that go through the valve. So instead of a valve being halfway open at 50% of the control signal, we're now going to receive a specified number of GPMs every time we go to that same control signal. This is a vast improvement over position control valves, and that gives us much better control over our coils. Let's take a look at some of the advantages of using flow control. First, let's start with examining how coils work. You'll notice that this coil curve that is being displayed here shows us flow on the x-axis and coil power on the y-axis, and that it has a somewhat bowed shape to it. It is not linear in nature, and therefore it is a difficult shape to control. So a valve is designed to behave equal and opposite from the way a coil might behave. So valves will open very slowly, whereas the coil operates very quickly at low flows. This is in place so that if I trace out my valve being only halfway open, I may only generate 20 to 25% of my flow. But that 20 or 25% of my flow may gain me indeed about 50% of my BTUH exchange into my space. The net resultant of these two curves would be that the control signal related to coil power would be somewhat linear in nature, and that is what we're able to control with our coil. This is why most control valves have what's known as an equal percentage flow characteristic, so that we are equal and opposite to the behavior of our coil. Let's take a look at a few things that are wrong with valves that utilize position control, because frankly, the valves that use flow control operate much more how our brains think that all valves operate. We're going to take a look at pressure-dependent valve in terms of how low delta T is generated in the coil. We will also look at points on the coil curve where additional flow no longer nets us any more heat transfer, and then we'll talk about the difference between static and dynamic balancing within our system. Let's start with a little bit of math. This is the formula for flow coefficient, and this is how we would size a standard pressure-dependent control valve. CV, or flow coefficient, is equal to the required GPMs of the coil divided by the square root of the design pressure drop. This pressure drop is typically defined by the engineer. A valve will be selected based on the CV that is calculated with this formula. Once the valve is purchased, however, that CV, or flow coefficient, becomes a fixed number. So let's say I bought a valve with a CV of 10. If the design pressure drop is about 4 psi, that means I'll get a certain number of GPM every time I give it 4 psi. However, if that same valve sees 10 psi, I'm going to get a much higher flow. This is what we talked about earlier as one of the flaws of pressure-dependent or position-control valves. So assuming that when I have a high pressure drop, I overflow my valve, let's take a look at how that affects other things in the space. The power output formula for our coil on the water side is equal to 500 times GPM times delta T. In this case, if the GPM is flowing higher than is prescribed and the load in my space doesn't change, well, that's what causes low delta T. Flow and delta T are inversely proportional at the coil when my load is fixed. Let's take a look at our coil curve again. Notice that as we get towards 70, 80, 90, and even 100% of the flow, the coil curve starts to plateau off, not generating nearly as many BTUs percentage-wise as I was at lower flows. So the question is, what happens when we overflow that coil? Well, we are penalized in 3 ways when we overflow that coil. We're going to pump additional water, obviously, to get it in there. We're going to reduce our delta T, and we're not going to create any additional BTUs. So this is what we have termed as a waste zone. The waste zone is an area where we're pumping more water but not achieving any more performance in the space. A flow control or pressure independent type valve would allow us to avoid ever entering the waste zone by stopping all flow at 100% of the coil design. Let's also take a look at balancing. Static balancing is the traditional balancing technique and can cause a lot of problems in your hydronic system. Let's take a look at 2 loops, one close to where we're pumping and one further away. You'll notice that the loop further away has a smaller pressure drop across the entire branch run than the one closer to where we're pumping. Assuming that the coil and the valve are the same in both of these, let's take a look at how this would be balanced. In a traditional balancing technique, the pump would be ramped up to 100% and the valves would be open all the way. At this rate, the loop far away, the coil is taking a 4-pound pressure drop. The valve was sized for 4 pounds of pressure drop, and we'd like to maintain that, and therefore the balancing valve must be adjusted to accommodate the other 2 psi, so that I have a total of 10 psi across my branch run. So far from the pump, I have a low branch differential and a low pressure drop on my balancing valve. As I get closer to where I pump, I have a larger branch differential. But I still have the same coil, and I still have the same valve, and I have the same pressure drop design on the valve as I did on my far branch. So the coil and the valve still take 4 psi, but now I must set my balancing valve to take a much larger pressure drop of 12 psi in order to balance this loop. So closer to where I pump, I have higher branch differentials, and I have a high pressure drop on my balancing valve. Let's take a minute to discuss what balancing valves really do. A wide open balancing valve essentially creates no pressure loss in the branch run. It actually creates a very small pressure loss, but for this conversation we'll just assume that it has none. The blue circle on the right illustrates a pipe cross-section with the pipe wide open. So at 100% of the flow rate, a wide open balancing valve will essentially create no pressure drop. If I turn my balancing valve and I begin to close it some, what I'm doing now is shrinking that area of the cross-section of the pipe. I'm taking the same amount of water, 100% of the flow, and I'm pushing it through a smaller space. This is what causes that pressure drop. In this case, we'll make the assumption that we're taking the 12 psi pressure drop required in our branch run that's close to where we're pumping. The question is, if I don't have 100% of the flow, how much pressure drop am I still taking? Assuming I may be only flowing 20% of the flow rate, there's no way I could take a 12-pound pressure drop through here because the reduced area is plenty of room for 20% of the water to go through there. In this case, we might see only a 1 or 2 psi pressure drop instead of the 12 that was there when we balanced at full flow. So going back to our branches, let's take a look at how our balancing's working out when we're only at 20% flow. At the coil, far from where I'm pumping, I'm still taking a 4 psi drop at my coil. It's actually probably a little less than that, but again, for this conversation, we'll say it's still 4 psi. Remember earlier that the balancing valve was scheduled to take a 2 psi drop, but now it's probably taking 1 or even no pressure drop. That means that all of the rest of the pressure drop from this branch, in this case 5 psi, will go to the control valve. So far away from where I'm pumping, I'm going to generate a small overflow. I sized and balanced the valve for a 4 psi drop, and now it's seeing closer to a 5 psi drop. But closer to where I pump, I run into larger problems. Let's say again we still have 4 psi on the coil, and now our balancing valve, which was supposed to take a 12-pound drop, is probably only taking 1 or 2. In this case, we'll say 2 psi. That means that the entirety of the rest of those 14 psi go to my control valve. Here I'm going to generate a massive overflow. Again, this valve was sized and balanced for a 4 psi drop, and now it is seeing 14. You can see why static balancing can cause a lot of problems. We don't spend a lot of time with our system operating at 100% pump with our valves wide open. Indeed, most of the time we have our pump at a reduced rate and our valves are modulating through a mid-range position. Flow control or pressure-independent valves have a great advantage when it comes to balancing because there are no balancing devices that go in next to a flow control valve. And in fact, they are completely dynamically balanced as they operate normally. What this means is that our pressure-independent valve, or our flow control valve, is going to put the exact amount of water to the coil regardless of what happens around it. In this case, far from the pump, I get the exact GPMs required for my coil. And close to the pump, I get the same exact GPMs required there as well. By dynamically balancing, it doesn't matter if I'm at low end of my pump range or full pump, or whether my valve's almost closed or all the way open, we're still going to stay at the exact prescribed flow rate, and therefore we'll have no fluctuations in our system due to balancing problems. Let's head back to the evolution of our control valve. Remember that we started with position control, and this gave us a lot of problems because we were not able to control the pressure necessarily that's coming to our valve. From there, we went to flow control style valves, which are pressure independent in nature. And this was a great advantage because we're no longer overflowing our coils and we're able to dynamically balance our system. But the one thing that we don't have control over when it comes to flow control valves is other parameters in our system, such as temperature. The Belimo Energy valve also has a module that allows it to control directly to power or BTUH into the space, and this makes the valve temperature and pressure independent. What do I mean by temperature independent? Well, temperature independent means that slight variations in the supply water or even the supply air temperature no longer affect the BTU exchange into our space. The valve can detect these immediately and make changes to how much flow is required to meet the load in the space. The Belimo Energy valve is able to operate with any of these control modes. It can be set to operate in position control, flow control, or power control. Let's take a closer look at power control. Remember our curves from earlier on in the seminar? This was our coil curve with a steep early behavior and a flat late behavior, and we were measuring flow versus coil power. Then we put in our control valve, which had a slow opening action, and this related our control signal to our flow, and we were hoping that the sum of these two curves would give us something where control signal was controlling directly to coil power, and we were hoping it would be a nice linear relationship between the valve and the coil. What's beautiful about this is that this black line here is power control. I indeed no longer care about the characteristic of my valve or my coil. Power control essentially makes the valve and the coil into a single piece of equipment that we control directly from measured values. Let's take a look at an example of how it works. Assuming we have a 0 to 10 volt signal, and that would correspond to 0 to 100% of the BTUs per hour capacity. If we had a 1000 kilobtu per hour coil, and I sent a control signal of 3 volts, that would relate in 300 kilobtus per hour. 7.5 volts simply equals 750. It makes it quite simple to control our space. Now each time the control signal is modulated, 10% more control simply means 10% more heat exchange into the space. In addition to better control, as I said earlier, this allows us to avoid temperature problems within our system. So supposing that my supply water temperature was a little bit warmer than design. Suppose I'm expecting 42 degree water at my coil, but for one reason or another it makes it there at 44 degrees. Well, 44 degree water is not going to produce as much BTU at the same GPM as 42 degree water, and therefore I will have less BTUH exchange into the space, and ultimately I should disrupt my discharge air temperature. When that is disrupted, the control system will notice this disruption and send a signal to the valve to supply additional water. Since the Belimo Energy valve in power control mode is already measuring BTUH, it will sense the BTUH reduction long before the discharge air temperature is disrupted and make that correction without the control system having to be involved. A similar result would happen if the air that arrived at the coil was warmer than design as well. So to review our two control modes, we discussed flow control, which is pressure independent and prevents overflows in our coil and allows us to dynamically balance our loops. Power control is pressure and temperature independent and let the valve and coil work as a single unit, and this gives us improved control over our space. Thank you very much for joining me today on this Belimo webinar. To learn more about the Belimo Energy Valve, please go to our website www.energyvalve.com or reach out to a local Belimo representative or distributor. Thank you again for joining us, and if you have any questions regarding this webinar, go ahead and forward them to marketing@us.belimo.com, and we'll get you an answer just as soon as we can. Thanks again, and have a nice day.